dynamics and control. So all I know, I've gone through different equations and all. And initially I thought of giving again modeling because my area is humanoid robotics and I have done the stability analysis, all dynamics, kinematics and all of this robot, humanoid robot. But then I thought I will be getting only 1 hour. So a little bit about stability, just theory. If you are showing the demo, what are the theory behind this, the stability, and those things will technically, little bit technically will see. And I'll explain. Those who are, I don't know whether I will be getting another session for explaining kinematics and dynamics of humanoid robot. So what I will do is, I'll explain because you have some knowledge about how to model kinematically, how to model dynamically, and all based on that knowledge. So this humanoid robot, how can you model? Because you have learned or you got the lecture related to the serial manipulator. But if you are having a humanoid robot, if you are going for modeling, you can do the model by considering the system as a serial manipulator. That you will learn. And the same manipulator, you can model in the other way. You have to assume that system as a parallel manipulator. So the parallel manipulator modeling and all, you are going to see kinematics in the afternoon session and dynamics tomorrow morning. So that you will get idea only after learning those concepts. But I'm not going to the equations and all, but I will explain how to model that serially and parallel. And before that we'll, and another thing, but I don't know whether, you have idea, you know that you have gone through the kinematics and dynamics. Just asking the physical or meaning of the kinematics. You know the why we are going for kinematics and why we are going for dynamics. See, already the experts, even Sudheer also explained why the dynamic model is important. See, generally we know, even the students are doing or designing or controller, we need a dynamic model, require a very good dynamic model. But generally the people, I'm not blaming anybody, maybe for electronics or electrical people, what they will do is they will take the model directly from the paper and they will do the controller design. So that will create problem actually, because if there is any slight modification if you want to make in the model, you should know the model. That's why this platform is open to all branches, not only mechanical. So electrical and electronics, all participants should know how to model. The people should know how to model the robot dynamically. And so that whatever the modification required, that you can do, and based on the model, you can do the controller design. So the first objective or first importance of dynamics is the number one, you can, if you are having a complete dynamic model, you can do the controller design. That is the first thing. Another thing, if you are having the dynamic model, so if you are having some other idea you can add. So if you are having a dynamic model, see, generally the people, what they will do is they will select actuators just like that. See, they are not, maybe even some students what they are generally doing, after designing the mechanism, if you want to integrate the actuator different joints, what they will do is they will integrate the actuator by trial and error. That means they will take one actuator and they will fit. They will check it whether they will work or not. If it's not working, they will take the another one and they will fit and they will check it. Finally they will get a system, that is actuator, but that's not the right way. So you will get an idea that this much torque is required to drive the mechanism. So for that, what you can do is, if you are having a dynamic model, definitely there are a lot of assumptions in the modeling. Though the system is rigid and joint is rigid and there are a lot of assumptions. What you can do is you model the robot dynamically, then you plot the joint based on the joint parameter you plot the torque values, and while in based on the workspace constraints, theta is joint, moving so and so angle, you plot it. Then if you are plotting the torque based on the different joint values, then you will be getting the torque variation at torque variation at different joints. So you will be getting the torque graph, and you will be getting the variation of the torque, and you will be getting minimum maximum torque at different locations. So that is the theoretical torque, maximum theoretical torque required for a particular application. See, if you are going for different applications, definitely required. I am just giving the idea, that's all. So then you will be getting the torque values, and that torque value is the theoretical torque value. So what you can do is, based on the complexity of the mechanism, you can assume the safety factor. So what you can do is, the actual torque will be the safety factor into theoretical torque based on the complex mechanism. That's what I was asking yesterday to Ashita sir. If the motion is quasi-static or static, why you going for dynamic model? See, sometimes it will be very difficult to model dynamically complex systems. So what you can do is, you can model the system dynamically, statically. Then if it is moving very slowly, the complex mechanism, what you can do is, you can assume the assumption may be double, 2. Then why are you going for the complex model? Then as Chandra was saying, you can go for the static, what is a balance? Static balance, static control, right? So so that is another thing. So you can go for the selection of actuator. If you are knowing that the actual torque, you have a data sheet for different company based on different comparison. You go for which type of actuator, so and so. Then you can select the actuator. That is number 2. Controller design, actuator selection. Number 3, as you know, if you are designing a function or a task, suppose if you want to pick an object from a point, then you can pick the object through some trajectory. You can go for trajectory planning. And if you are picking objects from one point, then either you can go for different, multiple solutions of the mechanism, and we have already discussed. So you can go for multiple path, right? So you will be getting a path with a minimum error. For example, if you want to take an object from here, you can take it. Suppose if you are going through this way, it will be difficult, right? So the human itself, the neuron itself, it will select the minimum power or energy path. So when you are designing, actually what you can do is, you can optimize the energy. So that's what sir was explaining, say optimum design. So optimum path. So the optimum path, in the sense that may be the optimum energy path, optimum power consumption, right? So if you want to pick an object, you can pick the object in such a way that the energy consumption is minimum. Then the power source will be durable, right? So all these things we have to consider. That is another aspects in that. So you can, if you are knowing the torque and all, you can you can find out the power and you can minimize the power and all. So these are some importance of dynamic analysis. The kinematic analysis. Kinematic analysis, inverse and forward kinematics. If you want to pick a object from this one point, you should know the inverse kinematics. And also, if you want to select a robot for a particular application, then you can go for 2 degree, 3 degree or 4 degrees of freedom. And for not only a particular application, if you are having, designing a robot for multiple applications, and based on that you have to change the degrees of freedom. See, there is some role on the selection of degrees of freedom in the kinematic analysis. And link parameter, maximum reach and all. And workspace analysis, if you are doing, where to reach, which are the position where the end effector will reach. So all these things, the kinematic analysis, important. Okay, so the significance of kinematic and dynamic analysis is, that is very important. These analyses are very important. That's why we included the kinematics, dynamics, then the control. Right? Now, I'm not going in depth about the equations, but we'll see. My area is bipedal locomotion. Then the one important thing is whether it's the classification. When we see the classification of robot, here in this program, we'll be discussing only parallel and serial manipulator. That is robot manipulators. Robot manipulators divided into serial and parallel manipulators. In addition, the second classification is mobile robot. In the mobile robot, it's a leg robot, track robot, mobile robot, and hybrid track, leg, then wheel, leg, and all. Right? So in this robot is coming under leg classification, leg robot, and that leg robot may be a 2-leg robot, 4-leg, 6-leg, 8-leg, etc. So very difficult thing is if the robot is in leg with 2, it's very difficult to get the stability. See, there are some robots. See, yesterday sir was showing, if you are kicking, it will come to the original position, right? That is 4-leg robot. There are some robots developed by the same company with 2-leg also. If you are kicking, the 2-leg robot will come to this initial position. But the problem is the cost. We cannot market that. So the importance of the stability is related to the foot size. Suppose the foot size of the robot, you see any robot like Asimo, you see Asimo itself, or HPR, or any humanoid robot, you can see the foot size. You can see the big foot size. The big foot size means there is a chance of self-collision, right? While it's moving, there is a chance of self-collision, and also there is a chance of collision with the environment. So our objective, my area, research area was how to reduce or how to optimize or minimize the foot size. If you are minimizing the foot size, you can avoid self-collision. Suppose you are bringing to a point. Bringing a point is very difficult, even though in simulation we can do, but it's difficult to bring it to that level. But to any terrain, robot can move. So that is another important area of research. When come to the stability, see what is humanoid robot? Humanoid robot or biped robot are the class of robots that imitate the human locomotion. Then there are so many robots you can see with different characteristics, different functions, even facial expressions, etc. You can see number of robots. These are some examples of robots. Leonardo robot, robots, Nio, etc. And here also the important thing is the dynamics. See, these are some examples. You can see the Einstein robot and with the facial expressions, and you can see the other robot, lady robot. You can see the facial expression. See, earlier in the modeling, I will show that model. You cannot see the robot with this, mathematically, in the model you cannot see this link. Why? Because in the olden times, you can see only this. This is not much important while moving, right? But the problem now, because for facial expression and all, you can see about more than 60 or 60 small actuators you can see inside the head. So the weight of this is also very important. Now in the modeling, that also should be considered. So in the bipedal locomotion or humanoid robot locomotion, you can see planar motion and spatial motion. See, the planar motion means either, see, the human is moving. You can see a plane here, that is known as the sagittal plane. So the stability, if you are considering while moving in that plane, you can say that is the sagittal plane stability, and you can call it as the planar motion. And similarly, if you are moving, lifting, then there will be a stability in this plane. Then that plane is the frontal plane. So when in the spatial motion, you have to consider two stability. One is the sagittal plane stability and the other is the frontal plane stability. The researchers are doing the stability analysis, that is the stable motion, by considering only the planar motion, either planar motion or the frontal motion. Only you can see the paper by this type of motion also. But the actual practice, or in real sense, the motion should be both sagittal and the frontal plane stability. And the stability, you can see the motion. See, generally there are two phases of human motion, humanoid motion. See, if the robot is moving, two legs are on ground, you can say that in double support phase, DSP. If you are lifting one leg, that is the single phase, single support phase. So if it is moving, so the complete locomotion consists of DSP and SSP. That is the single support phase and double support phase. And in the most of the researchers are doing, and even you can see the robot, while the robot is moving, you can see the foot is horizontal always. Because while it's moving, it's very difficult to control the angle, that is this one, because of more degrees of freedom. But now you can see there are some robots with this type of control also. But in these robots you can see it's moving horizontally. Then there are two single support phase and double support phase. In between you can see pre-swing phase, you can see that, and post-swinging phase. And that pre-swinging and post-swinging phase may be difficult, but you can see a lot of papers also, but that will be a little bit difficult. And the stability, if the robot is moving, there are two stability, there are a lot of other, two more stability criteria, but these two are important. One is center of mass, the other is ZMB, zero moment point. If the robot is moving statically, that is suppose instantaneous stability, if you are lifting, then the whole center of mass, the projection of center of mass should be in a projected polygon. That means we were having two, these are on the ground, and if you are lifting, it would be like this. So the center of mass, projection of center of mass should be within this foot. Then only the system will be stable. And this double support phase, then it should come within the projection, should come in the projected polygon. So the stability criteria is ZMB, projection of COM should come within the support polygon if the motion is statically stable motion. If it is dynamic motion, if it is moving, maybe that's what yesterday I was asking, how can we understand that the system is dynamically moving or quasi-statically moving? So is the dynamic moving, as sir told, we have a different, in state space model, we have different components, we can plot that and can find out. See, in which motion is dynamically stable, the another term is zero moment point, ZMB. That is, if it's moving, there are some active forces on different links of the mechanism, that is the human body. So all these moments of active forces should be zero. If the active forces should be zero at zero moment point. So that zero moment point will be taken as the on ground, and that zero moment point also should come within the support polygon in the dynamic stable case. In statically stable case, COM should come within the support polygon. In the dynamic stable case, ZMB should come in the support polygon. These are the two stability. If it is coming outside, system will fail. It should not be stable. And see the type of stability. You can see in papers only two types of stability. That is the statically stable condition and a dynamically stable condition. In statically stable condition, you can see the ZMB, COM is moving in the same line. You can see the line. So because we have to consider only C here, because the motion is statically stable motion. But in the second case you can see the dynamically stable motion. The dynamically stable motion you will consider ZMB. But COM motion is outside. COM motion is outside, but ZMB will be inside the support pole. Then only system will be stable. And third case is important because as I explained you, the foot size is minimum. If the foot size is a point, you can see the pure dynamically stable motion. That should be our objective. If we are getting the pure motion, then you can send the robot to any location. But that's difficult. Now come to, with this idea, because we have shortage of time, with this idea we will be starting the demo. Before that I will give you a small idea about this particular robot. See this, these are the manufacturers and these are the details. Then the Nio is 58 centimeter tall and see the 5 kg humanoid robot. And degrees of freedom and details are you see the recognition object, poster and gesture recognition, environment recognition, sound recognition, these are the capabilities, face recognition. And you see the degrees of freedom, head is having 2 degrees of freedom. Head is having 2 degrees of freedom, arm 5 degrees of freedom, then the pelvis 1 degrees of freedom, leg each 5 degrees of freedom, and hand only 1 degrees of freedom. So these are the different sensors attached to the system. And see, one by one, you can see the infrared sensor, the emitter. You see the first and other figures. You can see there are different sensors, locations and all. You can see from this robot also. You know the different functions of different sensors. And see, as I explained you, this while it's moving, you have a control loop, right? So the ZMB, as I explained you, ZMB, while the robot is moving, you have to determine the ZMB or center of pressure. And that center of pressure, how can you find out? For finding center of pressure, you can see these are 2 4 and 4 sensors are attached at the 4 location. Then while lifting, you can locate the center of pressure, right? So that's why 4 sensors, FSR sensors are attached below the foot, so that you can while it's moving, you will get the location of ZMB or center of pressure. Then that can be used to get the stable motion through feedback loop. And these are the different hearing and touching. There are different sensors attached at different locations. And you can see that during the demo. So this is 25 degrees of freedom robot. And it has capabilities of feeling, hearing, speaking and seeing. And it will interact, this will interact also. And then these are the basic idea, component details. But as I explained you, just I will explain how to. I explained you how if you are having a model, robotic model, how to consider that as a serial robot, as a parallel robot. Just 5 minutes. See, this is what I explained you. Then planar motion, you have to consider as a link. Then upper link, you can see J4B. J4B generally in most of the people they don't see that link. In most of the, why? Because this link is important if the weight is more. Otherwise, no need to consider. Generally, it's considered as the one link. But link weight is more because suppose if you are designing a spatial robot with a spatial expression and all, and you have to fix maybe more than 60 or actuator, then total weight will be more. Then such cases you have to use that. So you can do that, you can consider this as a
a planar robot, and you can analyze this. The stability also you can analyze based on static stability or dynamic based on ZMB or COM. Then this is what I have done. Just explaining. This is a motion, but these are some equations for finding ZMB and all. I am not going to see. You see this robot. This robot is a spatial robot. I am just a bipedal robot. Only the robot. I mean, you have hip and the bottom motion. It's a 12 degrees of freedom robot, biped robot, and you can model it. See, this is the DH modeling. No, DH modeling we have already. You know, and you can, based on DH model, you can model it so that you will get 12 DH parameters, a DH set of parameters, and you can see what you can do is, suppose you have you have two legs, and while lifting, you can consider this as open, right? Open. So this is a serial manipulator. Serial manipulator, and you can fix the frame, zero frame to the end effector frame, and you will be getting the DH model. DH model. Then you can move from, maybe if you are having a path, a trajectory, cycloid or cubic, you can move it this, then it will reach the next. If you are taking the next step, what will you do? You consider this as the ulta, you consider this as the zero frame, then this will be open, right? Then like that you can. So see, this is the frame and this is the end effector frame. Then this is open. While it's moving, fix it. Then next step, this is fixed, then this is open. Same model. Same model. Like that you can do the kinematics. And same dynamics you can do either, you can go for Lagrangian, but Lagrangian will be difficult. I have used Newton-Euler formulation, but Newton-Euler formulation is not explained here. That's why I am not going to explain that. But you can use both Newton-Euler formulation or Lagrangian. And see, this is just simulated result by a student. So you can see the first two. In first two, that the first one is the single support phase, and next is a double support phase. Just lifting. See, like this. Then you have to shift. Then this is a parallel mechanism, right? So in the complete, if you want to, simulate the complete model, if you are lifting like this is single support phase, and you have to lift, then that's a double support phase, and that double support phase you can consider as a serial manipulator. You know the 4-bar mechanism, right? 4-bar mechanism. Same way you can consider, and you can consider as a serial manipulator, parallel manipulator, or you can consider the both cases as a serial manipulator. But the problem is you have to go for so many other assumptions. Like that you can. So then this is step lining, but you can see this single support phase, and while it's moving, the hip is moving like this, right? Hip is moving like this. So that's why it's. But you can bring to the closed. The closed. If you are giving the closed constraint, for example, theta 1, theta 2, theta 3, etc. Within this limit, you can bring it to the actual level. But the problem is that you will be getting from the literature only, because while it's moving, how much will be the range of different actuator angles. Then based on that you can fix it, and you can find out the angle, and you can simulate it. And each motion you can check the ZMB plot. See, what I have done is, see that this is a ZMB plot I have made while moving, during single and double support phase. And you see the ZMB is moving at the foot, the size is moved. What I have done is, I just simulated, but the size you have to reduce. That is one part of my work, and the variation of ZMB is more because while it's lifting, the hip is moving like this. So lifting, hip is moving like this. That motion you can adjust by using the closed constraints. So these are the experiments I have done here for motion. Thank you. So next, Mr. Rahul will explain, demonstrate this. Rahul is a passed out student, electrical. and I mean, we have a robotics interest group here. He was the leader of the group to the last year, and we are doing lot of work here, small level to the higher level. Anyway, you will be getting a demonstration mostly on Friday to the lab, and you can come and see that. Our students will be demonstrating the project. And Thursday, our PhD scholar, Srikanth, he is a faculty, Dada College, and he is going to give you the lab session, a 3 hours lab session, and it will be very useful. It will be very simple, it won't be a complicated one. And also all the faculty should know how to control an actuator and all by using different microcontrollers and all. So very simple way we'll try to explain with 1 or 2 links, then that will be helpful to guide your students or like that. So we'll try our level maximum to come down. So if you're having any problem and all, you have to inform the coordinator, myself or Joyce sir. Okay, so he will be explaining that, he will be demonstrating the robot. Thank you.
Good afternoon all. This will be a brief, very short demonstration of the Navo robot. It's a French make, as you have seen it in the slide. It costs around 10 lakh rupees, and it's a new addition in our robotics lab at the institute. So here the basic. Okay. So what we are going to do is, this is basically, it will be having an embedded processor inside it, and it's connected to all its actuators and the motors, as well as for sensory feedbacks, all the sensors. It has around 4 microphones and speakers, along with 2 HD cameras, then other actuators, and then it has tactile sensors at its feet as well as in its head, so as to detect any objects around the way or things like that. So this is basically programmed using a software that is already provided by the manufacturers called Choreograph. So it is something similar to this MATLAB Simulink environment, where, especially the Simulink environment, where you can actually drop all the blocks and connect it using the wires, and you can do the programming. So that is one way of programming the Navo robot, and which is currently now being used. Otherwise, you can write shell script or C++ program, Python or etc. and compile it, and also you can upload it. So the way how we connect it is that the connection from the laptop to the robot will be through Wi-Fi. Our laptop, the working laptop, will be connected to a router, and the Navo is connected through Wi-Fi towards the router and hence to the laptop. So that every time the new program is being made, it has been uploaded to the Navo or Wi-Fi. Okay, so this simple demonstration will include, it will be greeting you all initially, and then followed by it will be taking a human guide, turning towards you, sitting down, standing up, and some activities. So let's. Sudheer, just in case if it falls down on the thing. Okay, so I'm going to run the program now.
Hello and once again welcome to National Workshop on Robotics and Control here at National Institute of Technology, Calicut. You must be wondering who is talking. Well, look over here. Here I am standing. I am now. It is a pleasure to meet you all. I will be helping out Sir in his talk on humanoids and pivotal stability. So let us begin.
So I have programmed in such a way that the robot is supposed to move forward for something around 40 centimeters. Then it should stop. Then it should turn towards your side. Then it will be again moving forward for another 40 centimeters or so. So you can see how the human motion is being recreated here. Now it will be performing to sit down. You can see how the robot is programmed. So it will be sitting down there for a while. Maybe I have given a delay of some 2 seconds. So you can see that the robot is looking for where the sound is coming from, or if it catches attention of someone in its camera, the robot's face will be following it. That's what you see when Sal was taking the class. The robot was actually facing to it. So its writing is.
Oh, that was a lot of work. Thank you. Well, next I have something for you. Enjoy.
So now I have something surprise for you. So you can see that it's actually standing in just one speed now.
Thank you all, and thank you, sir. Hope you all enjoyed it.
So that is a very small demonstration from Navo. So apart from these functions, it can, what else you can do is that, I don't know if it will work in this small area, you can actually play a soccer game also. So if you provide, now it's been configured for a red ball, so if you show the red ball initially, then when you keep it on the floor, so it will be able to detect where the ball is, and then once the ball, gets near its feet, it will be able to feel it using this tactile sensors over here. So once it is feeling it, it will be picking it. So maybe I will just give it a try right now. I don't know whether this space will be enough for it.
Let me get ready to kick the ball. Just a second. I got it. I want to play soccer. Show me your red ball when you're ready.
Now has asked for a red ball.
Started. I need to measure the ball. Keep it between my hands. Thanks. Let's go. Hello and once again, welcome to National Workshop on Robotics and Control here at National Institute of Technology, Cap. Let me get ready to kick the ball. I got it. I want to play soccer. Show me your red ball when you're ready. Good. Before starting, I need to measure the ball. Keep it between my hands. Thanks. Let's go.
So actually this ball is very light, so usually a little more heavy ball is preferred, because once it touches the ball, actually the ball will start moving. If it was a little heavy one, then the ball would have been still standing there and will now would have been able to kick. No, if it actually when it's on the ground, I think it's not clear to see. I don't know whether. Yes. Now, suddenly what happens if the Nava robot, somehow
Where is this ball hidden?
falls back?
Where is this ball hidden? Oh, what am I doing on the floor? Ugh. Ugh. Hey, I'm back. That's much better.
Now what if Nava was walking straight forward and suddenly falls down? See, you see, when it suddenly falls down too, hands come in to support it.
And that's it. Back on my feet. I feel better with that.
Thank you. That's all for the demo.